Hey, this video is part of a video series. I will talk about the main concepts, but there's also another video where I'm talking to Karel Heni, our research scientist, about ideas for how to extend this work, criticisms, and potentially useful mental models. So go check out the interpretability QA as well. Hello and welcome. Today we will talk about a paper called Polysemiticity and Capacity in Neural Networks. We will explore how models allocate limited representation capacity, and we will have a look at what polysemiticity is and how it differs from superposition. Let's get started. To start off, I want to answer the question what the authors did and why it's useful. So first of all, the authors use a toy model in which they analyze how feature importance and sparsity affect the occurrence of polysemiticity. Doing so is useful because this toy model allows you to have the testbed to develop new interpretability methods. These changes might include changes to the architecture, to the loss function, or simply the activation function. A core concept in the paper is the concept of polysemiticity. And what I want to do here is explain the difference between polysemiticity and superposition. What it means for a neuron to be polysemantic is that it fires on distinct concepts. So rather than one neuron corresponding to one feature in our data set, it corresponds to multiple. Now we can see two distinct reasons for why this could happen. Before we dive into this, I want to explain briefly how to read this plot. So on the x-axis you have neuron 1, and on the y-axis you have neuron 2, and then here you've got features. And so in a rotated embedding, these features do not line up with the neuronal axis, right? So they don't line up with the neuron bases. And so if I read out, let's say neuron 1, or I read out neuron 2, I project the features onto that axis, right? So again, reading out a neuron means that I'm projecting these features onto this axis. And so as you can see here, if I were to read out neuron 2, I'd project feature 1 onto this axis and feature 2. And that would basically make it much harder for me to interpret this neuron. The other thing might just be that the features are embedded non-orthogonally. As we can see here, they were embedded orthogonally but rotated. In this case though, we have non-orthogonal embeddings. So the feature 2 here actually lines up with neuron 1, but feature 1 doesn't line up with neuron 2. If we were to read out neuron 1, we would also incur polysemanticity because we would get a strong signal from feature 2 and from feature 1. If we were to show this pictorially, we would get a picture that looks like so, where the colored dots correspond to the features, the white dots correspond to the neurons, and the lines between them correspond to the weights. In the ideal case, we would have neurons line up with the standard bases. And that would mean that each feature would line up with one neuron. And pictorially, this would look like so, where feature 1, for example, lines up with neuron 1, and feature 2 lines up with neuron 2. Having discussed polysemiticity, let's have a look at how it's different from superposition. In polysemiticity, what we observe is that the features don't line up with the neurons, even though they might have an incentive to do so. In superposition, the superposition hypothesis says, well, the features can't really align with the basis because there's simply too many features that we're trying to put in the embedding space. The superposition hypothesis has been studied extensively by Anthropic, and in this plot they summarize their findings. We have two important parameters: the feature importance, that goes from most important to least important, and we have the feature sparsity. What we can see here is that if feature sparsity is low, we will only represent the most important features, and all the other less important features will map to 0. Then, as we increase sparsity, our model will choose to embed more of the non-important features. And finally, at very high sparsity, we will see that the model will try to fit in all of the features into the space at the cost of interference. To make these rather abstract concepts like feature sparsity and feature importance more tangible, I want to draw your attention to an example here. So let's suppose we have a data set that consists of these 4 entries. We basically have these 4 pictures. The first picture contains feature 1 and only the circle feature is active. In the second image, we see that the circle, the square, and the star features are active. Then in the third, almost all the features are active, and in the fourth, all of the features are active. To answer what it means to be sparse, let's have a look. If we were to count the occurrences of each of the features, we'd get the following result, where the red dot feature is very present and so dense. In each picture, we basically have a red dot, and then the probability of the other features drops off. So on this end, we have a very dense feature, and on this end, we have a very sparse feature. Okay, so I think that makes intuitive sense as well. As a feature is more present in the data, it's much more important that we get it right and that the model learns to represent this feature so that downstream it can get low loss. Another mental image I find useful is the following, where if you think of a dense feature, then the probability of that feature occurring is high, and when you have a sparse feature, the probability of the feature occurring is very low. Now on to feature importance. Here's an example that illustrates this kind of nicely. So let's suppose we have this smiley face and we were to remove the ability of our network to detect a certain feature. If we were to remove its ability to detect circles, well, then it would only detect the following, the nose and the mouth. It would be hard to tell whether this is an arrow or a smiley face. However, if we remove the vertical line detection feature, it would still be able to recognize all of the rest, and hence it would still be able to classify this properly as a smiley face. Let's make an example to bring all of these points home. Consider a data set of images that has these features, and now let's say we have a neural network where we feed these images to the neural network. There's a hidden layer that contains, let's say, 4 neurons, and then there's an output layer that will make the final prediction. How I want you to think about neurons is basically as feature detectors. So if a feature is present and the neuron detects it, it activates. What I mean by that is basically that the value of the neuron is higher than 0. Consider this table. In the rows, we have individual neurons, and in the columns, we have the individual features. So the table shows which features the neuron activates on, meaning when a feature is present in the data, the neuron will have a value higher than 1 when it encounters that particular feature. And so here, it is clearly seen that neuron 1, for example, activates on more than one feature, right? It activates on this yellow rectangular shape and this blue square. And so this is a polysemantic neuron. Similarly, neuron 2 also is a polysemantic neuron. Different to those, we also have monosemantic neurons that only activate on one particular feature. So neuron number 3 activates on feature 4 only, and neuron number 4 activates on feature 5 only. As we'll explore later, these features will be said to have high feature capacity, meaning that they get their own neuron and that they will be monosemantically represented. Features that have lower feature capacity will be represented by polysemantic neurons. Okay, so with that in mind, let's revisit polysemiticity and superposition. So as you can see here, we have this two-dimensional space, and so in theory, we could align each feature with the standard basis. So the blue feature could get the x-axis, and the red feature could get the y-axis. In the superposition hypothesis, we hypothesized that the number of features is just too high for us to embed them orthogonally in the space. So it should be obvious at this point that 3 features cannot be embedded in a two-dimensional space. So to contrast what Anthropic was studying in the paper where they introduced superposition and what Redwood studies in this paper on polysemiticity, this is what it looks like. Anthropic basically studied how you can take a feature vector, compress it, decompress it, and do so with minimal information loss. Redwood, on the other hand, is interested in studying how a smaller number of polysemantic neurons can simulate the computation of a network that has a larger number of monosemantic neurons. Just so you know how to read this, the circles that have one input only are monosemantic, as you can see here, and the ones that have multiple inputs, as these, are called polysemantic. Okay, cool. Now that we've talked about polysemiticity and superposition, we can move on to the next concept that is crucial to understand this paper, which is feature capacity. Feature capacity, as defined in their paper, is the fractional dimension each feature consumes in the embedding space. Okay, let's back up and see what that means. Let's say we have a weight matrix that lives in Rd. Now this will be a d-dimensional vector that dictates the maximum capacity that we can allocate. Think about it this way. In a two-dimensional space, you can have a maximum of 2 orthogonal vectors, and in a three-dimensional space, for example, you can have a maximum of 3 orthogonal vectors. To illustrate this, here's a nice little example. Again, we have a feature vector and we are projecting it down into a three-dimensional space. This three-dimensional space limits our maximum capacity, and so what we'll see here is that some of these features get their own neuron, like the blue one and the yellow one. These will be called monosemantic. And then there are also some impurely represented features, like the black one and the red one, which get mixed into this polysemantic neuron. Also note that the model can choose not to represent a given feature if it's not important enough or too sparse. For those of you who are interested in how this would look like in matrix form, you can look at this picture here and verify for yourself that this is in fact what's going on up there. Also, for those of you who are interested in thinking about this for yourself and how feature capacity works, try to convince yourself why these examples are correct. Moving on, we have a rather full plot that will hopefully make sense in a while. Let's look at how the authors analyze the allocation of capacity that a neural network has to its disposal. This here is a budget allocation plot. On the x-axis, we see the capacity, and for each feature, we can basically give it a maximum capacity of 1. And on the y-axis, we see the marginal benefit. So what is the reduction in loss given that I change the capacity by a bit for a given feature? Now we can see 3 regimes here. These features that don't get allocated any capacity at all. Then we see this regime, this green one here, where the features are represented polysemantically. And then we see this regime where each of the feature gets its own monosemantic neuron. So given all of these together, we can sum them up and get the total capacity that this network had at its disposal to allocate. And in this example, it's about 8.5. As a final note here, the way that you interpret these downward slopes, these convex slopes, is that they correspond to diminishing marginal returns. So at this point here, the reduction of loss that I can achieve by adding a tiny bit more capacity to this feature is pretty high. As I move on and have, let's say, already allocated 0.6 capacity to that particular feature, the total reduction in loss that I can achieve by changing the capacity that I allocate to that feature is quite a bit lower. Also note that the features that get polysemantically represented all have the same marginal benefit on reducing the loss. The authors take the insights from this plot and try to visualize it in a different way, relating the feature sparsity and feature importance to how much capacity gets allocated. To understand this better, we will have to look at phase diagrams. Here's a simple example of a phase diagram of water. On the x-axis, we have the temperature in Celsius, and on the y-axis, we have atmospheric pressure. So as you can see here, there are basically 3 regimes. We have water in its liquid form, we have ice in its solid form, and we have water vapor in its gas form. We can double check that the plot makes sense by looking at the 100 degrees temperature mark at an atmospheric pressure of 1. This corresponds to the normal boiling point of water, and this corresponds to our everyday experience as well when we heat up water in a pot. If, on the other hand, we look further down here, where the temperature is close to 0, also at an atmospheric pressure of 1, we have the normal freezing point. Now, what is interesting here, for example, is that as we increase the atmospheric pressure, we will have to have a lower temperature for ice to emerge. With the basics out of the way, let's look at how the authors analyze feature sparsity, feature importance, and how much capacity gets allocated to a given feature. Whoa, okay, a lot is happening in this plot, but let's take it step by step. What the authors are doing here is they take two neurons, they fix one neuron's feature importance and sparsity, and then they take the other neuron and basically vary these two parameters. What we can see here then is the relative feature importance of the neuron, whose feature importance we are shifting around, and its feature density, or 1 minus the feature sparsity. What we then see here is how much feature capacity gets allocated. So the scale here goes from gray 0 to blue 1. And the way you would interpret this is, in this blue regime, the second feature gets allocated a lot of capacity, basically 1. In this gray regime here, it doesn't get allocated any capacity, so basically 0. And then in this red, pinkish regime, it gets allocated some feature capacity. Okay, so we have two features here. We have feature 1, which is this black kind of oval, and then we have feature 2, which is this blue kind of star. Let's say we keep feature 1 constant and we vary the importance and sparsity of feature 2. In that regime here, at points A and D, the second feature, the one whose relative feature importance and sparsity we vary, will not get represented. And this would look like so. We would get a neuron that only activates on the first feature. So it wouldn't activate at all on the second feature. Now, contrast this with the second regime, where we allocate a lot of feature capacity to our feature. In that case, we get a monosemantically represented feature. This means that the feature gets its own neuron that activates highly on it. In that case, the neuron would, for example, not activate on the black oval, but only on the blue star. In this regime, however, we can look at point E, where we can see that the feature gets allocated to a polysemantic neuron, which means that the neuron will activate on multiple features. In this case, we only have two features, so that would mean that the neuron would activate if it saw an example image that looks like so and only contained feature 1. It would also activate if it saw an image that only contains feature 2, or it would activate if it saw both of them. Another interesting way that we can look at this, that the authors propose, is by doing the following. We can look at this black curve, which corresponds to feature 1, which has constant sparsity and constant feature importance. And then the blue curve corresponds to feature 2 that has varied sparsity and importance. And these curves show us the marginal loss reduction for a particular feature given the allocation of capacity. Let us, for example, analyze point D. At point D, the marginal reduction in loss for feature 1 is so much higher than for feature 2 that we basically allocate all of our feature capacity to the black feature and no feature capacity to the blue feature. Contrast this with point F, where we have the opposite. We can also look at point E, where the marginal reduction in loss for the black feature is so much higher up until a certain point where there's parity between the reduction loss for the blue feature and the black feature. And that's exactly where these two meet. And so we will get a polysemantic neuron that activates on both of these. So now we are equipped with all of the necessary preconditions to understand the paper and the ensuing discussion. You can find the interpretability Q&A with Karel Heni in this video. See you there!